Have you ever felt ambushed by string windows? Find all anagrams in a string is a Pattern Mastery 100 essential that exposes whether you truly own sliding windows and frequency counts. Phong interviewers love it because a brute force check is too slow. But with the right window math, we get linear time and clean, confident code. Let's nail it with basics. Let's break this down. We're given strings S and P. We must return all start indices in S where the substring is an anagram of P. Only lowercase letters. The anagram condition means the character counts match. Now let's assess. Naively sorting each window is on middle.m log m, too slow. Instead, we maintain a fixed size sliding window of length len p over s and compare letter counts. 2 standard tactics. Keep 2 frequency arrays of size 26 and compare. Track a matches counter that says how many letters currently match p's count. We'll use arrays plus matches for O1 updates and ON time, O1 space. Here is the structure. Plan. Build need 26 from P. Sweep right over S, incrementing half C. Once window size exceeds len P, decrement the left char and move left ++. Maintain a match count. When have X equals need X, increment. When it stops equaling after update, decrement. If match equals 26, push left to results. Line highlighted, class solution. We define the solution class that holds our function. Pause. Line highlighted. If len p greater than lens, if p is longer than s, an anagram can't exist, so we immediately return an empty list. Pause. Line highlighted, p_count equals 0, 26. We create a frequency array for p's characters. Line highlighted, window_count equals 0, 26. This array tracks character counts inside the sliding window in S. Line highlighted, result equals, we'll store starting indices of valid anagrams here. Line highlighted, for char in P, we count how often each letter appears in P. Line highlighted, p_count ord char, ord A, plus equals 1. Each character is mapped to a 0 to 25 index and incremented. Line highlighted, for I in range len P, we fill the initial window of size len P. Line highlighted, window_count ord Si, ord A, plus equals 1. We count characters in that first window. Line highlighted, if p_count equals window_count. If the pattern and window match, we found an anagram. Line highlighted, result.append 0. So we record index 0. Line highlighted, for I in range len P, lens. Then we slide the window across the rest of S. Line highlighted, window_count ord Si, len P, ord A, equals 1. We remove the character leaving the window. Line highlighted, window_count ord Si, ord A, plus equals 1, and add the new character entering the window. Line highlighted, if p_count equals window_count, if counts match again, it's another anagram. Line highlighted, result.append I, len p plus 1. We store the current starting index. Line highlighted, return result. Finally, we return all the starting positions of anagrams. Highlight input box, S equals key b bobuct, P equals ABC. Let's test our function with the string p b bobuct and the pattern ABC. We're looking for all starting positions where an anagram of ABC appears inside S. Explain logic briefly. The first 3 characters of S, kaba, contain exactly the same letters as ABC, just in a different order. So index 0 is a valid match. Later in the string, the substring bok also matches the pattern, which starts at index 6. Highlight output box. Output, 0, 6. That's exactly what the program returns. 0, 6, matching the expected result. So the implementation works correctly. It finds every anagram of ABC by sliding a fixed size window across the string and comparing character frequencies. Now let's try another implement approach using solution 2. Shorter line-by-line narration, concise, clear, beginner-friendly. Line highlighted, class solution. We create a solution class to hold our method. Pause. Line highlighted, def find anagram self, S, P. This function finds all starting positions in S where an anagram of P appears. Pause. Line highlighted, if len P greater than lens, return. If P is longer than S, no anagrams are possible. Return empty. Pause. Line highlighted, p_count equals, window_count equals, result equals, we set up p_count to count chars in P. Window_count for the sliding window in S. Result to store valid starting indices. Pause. line highlighted, for char and p underscore count char equals p underscore count dot get char, 0 plus 1. We build a frequency map of the pattern. Time. OP. Pause. Line highlighted, for I in range len p. This initializes the first window of size len p and s. Pause. Line highlighted, window underscore count char equals window underscore count dot get char, 0 plus 1. We count characters inside the first window. Pause. Line highlighted, if p underscore count equals window underscore count, result dot append 0. If the initial window matches the pattern map, index 0 is an anagram. Pause. Line highlighted, for I in range len p, lens. Now we slide the window across S, one step at a time. Total. ON. Pause. Line highlighted. Left underscore char equals SI len p. Window underscore count left underscore char equals 1. We remove the leftmost char as it slides out of the window. Pause. Line highlighted. If window underscore count left underscore char equals 0. Del window underscore count left underscore char. If its count hits 0, remove it for clean comparison. Pause. Line highlighted. Right underscore char equals SI. Window underscore count right underscore char equals window underscore count dot get right underscore char, 0 plus 1. We add the new character sliding into the window. Pause. Line highlighted. If p underscore count equals window underscore count, result dot append I len p plus 1. If frequency maps match, we found another anagram. Add its start index. Pause. Line highlighted. Return result. We return all indices where anagrams of p appear in S. Pause. Final wrap-up. And that's how this algorithm works. It first builds frequency maps, then slides a fixed size window across the string, updating counts efficiently in 0.1 time per move. Efficient, simple, and elegant. Highlight input box. S equals key b bobuct. P equals ABC. Let's test our function with the string p b bobuct and the pattern ABC. We're looking for all starting positions where an anagram of ABC appears inside S. Explain logic briefly. The first 3 characters of S, kaba, contain exactly the same letters as ABC, just in a different order. So index 0 is a valid match. Later in the string, the substring bok also matches the pattern, which starts at index 6. Highlight output box. Output, 0, 6. That's exactly what the program returns. 0, 6, matching the expected result. So the implementation works correctly. It finds every anagram of ABC by sliding a fixed size window across the string and comparing character frequencies. Sliding windows can feel sneaky until you see the pattern. Find all anagrams in a string turns chaotic substring checks into a calm, linear pass with tight frequency math. Let's do a recap. We're given S and P, and we need all start indices in S where a length vertical bar P vertical bar substring is an anagram of P. Conceptually, match character counts, not order. Sorting every window is too slow. The right idea is a fixed size sliding window plus frequency counts. Maintain counts as the window moves so each step is 0.1. A small matches tracker tells us when the window's counts align with P. Build the target frequency for P. Sweep a window of size vertical bar P vertical bar across S. Add the right char, and when the window exceeds size, remove the left char. After each update, adjust the matches counter. When all tracked letters match, record the window start. We executed that plan. Pre-computed counts, slid the window with constant time updates, and captured indices exactly when the counts aligned. The solution ran cleanly on LeetCode with no errors. LeetCode verification confirmed the approach. Indices were collected correctly and all test cases passed as expected. Bullseye emoji. The lesson: sliding windows shine when you trade rework for maintenance. Keep counts in sync as you move, and anagram detection becomes fast, simple, and reliable.